This is section 7.5, applications of rational expressions. We've been solving equations that have fraction-like things in them. We talked about how to solve them in the last section. We talked about how to check to make sure that our potential answers did not give us a 0 in the denominator. Now what we're going to do is we're going to take that type of equation and solve word problems that create those types of fractions, so we need to know how to solve these. The first few problems are types of word problems we've worked before. It's just that fractions are going to pop up inside of them. Later, we are going to have a new type of word problem that we'll talk about. Okay, but first problem. In a certain southern state, sales tax on a purchase of $1.50 is 12 cents. What is the sales tax on a purchase of $9? Now, we assume that the rate of taxation is the same across the board. So what we can do here is we can set up a ratio. And as long as we are consistent on both sides, we can set it up a bunch of different ways. I could choose to put tax over price, or I could choose to put price over tax. Just as long as I do it the same way on both sides of the equation, I'm going to be good. Okay? So let's just take tax over price, just because it's the first one I listed. Okay, so we know the sales tax on a purchase of $1.50 is 12 cents. So I'm going to put 12 cents over the purchase price of $1.50. And this is going to equal. We want to know the sales tax on the other purchase. So the tax is what we're missing, and that's in the top. I'm going to put the X up here. And the purchase price is $9. Okay. Now we just need to cross multiply, okay? When you have a fraction equal to a fraction without an addition or subtraction or anything else off this side, we can cross multiply. But if we had x over 9 plus 7 or something like that, we would have to multiply by the common denominator, okay? Let's cross multiply. 1.5 times x, 1.50 times x is 1.5x. I'm going to drop those extra zeros, okay? Now you multiply 9 times 0.12 and you get 1.08. Divide both sides by 1.5. Okay, and then you get x is equal to 0.72. We were looking for the amount of tax on the $9 purchase, and that's what we found. The tax on that $9 purchase would be 72 cents. That's what we're looking for there. Okay. Next problem. Casey can travel 8 miles upstream in the same time it takes her to go 12 miles downstream. Her boat goes 15 miles per hour in still water. What is the rate of the current? Okay. What I see when I first read through this is I have a distance, I have a rate, and we're told it's the same amount of time. When I have those pieces, I know I'm probably using D equals RT. It's a distance problem. The distance is equal to the rate times the time. Now what's going on here is that we have some sort of stream. That's a very pretty river right there. And the water is flowing this way. And we know that sometimes she's going downstream and the water is speeding her up. And other times she's going upstream and the water is working against her. What I'm going to do is I'm going to set up a chart to help me figure out what's going on. Okay? We are given the distance for both. So if I'm talking about upstream, the distance traveled is 8 miles. If I'm going downstream, we go 12 miles. Okay. All right, so we know that the boat by itself is going 15 miles per hour. But in order to talk about the overall rate, we have to take into account how fast the water is going, okay? So let's say the water, which is the rate of the current, is going x, these are in miles per hour, so miles per hour. Okay, now the rate of the boat. We know it goes 15 miles per hour. It's just a question of whether the water is speeding them up or slowing them down. When we're going upstream, we're fighting against the water. It's slowing us down. It's slowing us down by x. So we take the speed of the boat and then we subtract off the speed of the water because that's how much it's slowing us down. Now the opposite happens when we're going downstream. When we're going downstream, the boat's going 15, but then the water's speeding us up. So this is 15 plus x. So we have the speed of the boat, and then we have here a representation of the speed of the current, and we're talking about how much it either slows us down or speeds us up. Now, one thing to keep in mind is that the water cannot be going faster than 15 miles per hour, because if it's going faster than 15, then we're never going anywhere when we're going upstream. Okay. So we have D, we have R. We need a way of talking about time. Now, we are told that it's the same amount of time. So if I can find a way of talking about this in math and then talking about this in math, I could put an equal sign between them and I have my equation. All right, so let's look at D equal RT. I have my distance, I have my rate. If I divide both sides here by an R, I see that time is equal to the distance over the rate. So the time here is going to be the distance, which is 8, over the rate, 15 minus x. The amount of time when we're going downstream is distance over rate. So this is 12 over 15 plus x. So we're told it's the same amount of time, so I'm just going to rewrite these with an equal sign between them. Okay, now I do have one fraction-like thing equal to another fraction-like thing. I'm going to put parentheses around my denominators so I can remember to distribute. It doesn't matter which order you cross-multiply with first. So let's just do 8 times 15 plus x is equal to 12 times 15 minus x. Okay, now let's distribute. 8 times 15 is 120 plus 8x is equal to, distribute here, 12 times 15 is 180, and then 12 times negative x would be minus 12x. Okay, so let's add 12x to both sides to get that over my x's together, and I'll have 120 plus 20x is equal to 180. Now let's subtract 120 from both sides, and we get 20x is equal to, that's going to be 60. Now divide both sides by a 20, and we get x is equal to 3. So we've solved our equation. Let's see what it is we were asked to find. We were asked to find the rate of the current, and the rate of the current is x miles per hour. So the rate of the current is 3 miles per hour. Now, does this make sense? Yes, it's a reasonable speed for water in general, if you just think about it. And it's not larger than 15, so the boat can actually make progress when it's going upstream. So this is our reasonable answer.